Okay. Hi, everyone.
Hello.
Hi. Okay, so any question about the previous sessions? No? Okay. So let's continue. Uh, we talked about overfitting and generalization and cross validation. At the end of the previous session, we entered L2 norm regularization, but we couldn't finish it. So let's start from L2 regularization again. So the L2 norm regularization is as shown here in this equation 24. So we have J, which is the actual cost, plus some regularization term. And alpha or alpha over 2 is the regularization parameter, right? And this is the L2 norm regularizer. So this is the regularized cost. When we have L2 norm for the regularization or for the penalty, that's also called Tikhonov regularization. And so now assume that the minimizer of the actual cost J is X star. Then according to first order optimality condition, what we know from high school, its derivative should vanish at that point. What do I mean by vanishing? I mean should be zero. So the gradient at X star is 0. So X star is the minimizer of J, not J tilde. Okay, now let's consider the Taylor series expansion of J, the actual cost. Okay, so I denoted by J hat. Then J hat is approximately by until second order Taylor series expansion. So it's approximately J plus this gradient and plus this second order. By the way, I'm evaluating the Taylor series expansion at the point X star. Okay, so interestingly, this term goes away because we know that according to equation 25, according to the first order optimality condition, goes away. And we only have the first term and the third term, where the third term has the Hessian in it, right? Okay. By the way, we know that this H is the Hessian of J, right? J. Okay. Now, so this was our problem, and this is our Taylor series expansion. Let's replace J with its Taylor series expansion. So we'll have these plus the regularization term. And now, so we want to minimize, according to this, we want to minimize this, right? With respect to X. It's an unconstrained optimization problem. What should we do? Take derivative, set it to 0. Hopefully we find a closed form solution, right? Otherwise, we should do gradient descent and this, or iterative optimization. So let's take derivative of J tilde with respect to optimization variable, which is X, and set it to 0. If we take derivative, what happens? Derivative, what is this? This is J at X star. So it's a constant because we have fed X star as input to the function. It gives us some scalar value, right? It's not a function anymore. It's just a value. Derivative of a constant with respect to X is 0. And then this is a quadratic form. Its derivative with respect to X becomes H X minus X star. And here by X dagger, I mean the solution. Okay, the solution of optimization. Then this is also a quadratic form, so its derivative becomes 2x. The 2's cancel each other, so I'll have alpha x. Set it to 0, rearrange the terms, and then left multiply the sides by h plus alpha I inverse, because this term is a pain in the neck. Then our x becomes this, equation 27, right? The solution. So x are denoted by x dagger, which is the minimizer of J tilde, right? Because I was minimizing J tilde. And does this equation make sense? Yes. Why? Because set alpha to 0. What happens? If alpha is set to 0, what happens? It means that I don't have any regularization term, right? So if alpha is 0, J tilde is reduced to J, right? Then if alpha is 0, the minimizer of J tilde should be the minimizer of J. Can it be louder? Because in this equation, set alpha to 0. This term goes away, right? Then we'll have J tilde equals J. So when alpha is 0, the minimizer of J tilde should be the minimizer of J, right? Now set alpha to 0 in this equation. Then X dagger becomes, let's do that. Let's calculate it. X dagger becomes H plus alpha I inverse. Sorry, there is no alpha. So it becomes H inverse H X star. What is H inverse H? Identity. So it became X star. So this minimizer of J tilde, which was X dagger, became equal to the minimizer of J, which was X star, as expected. Okay. Which one? Square and then 2. Which line? I don't understand. First. In the first line. This? First line. Yeah. Okay. X square is the power. What's the second square? Second 2. No, L2 normalization. X, this? Yeah. This is L2 norm regularization. So a squared L2 norm. We use a squared L2 norm. Why? Rather than L2 norm? Because squared L2 norm is convex. It's quadratic. L2 norm is not convex. Okay. And so this is a penalty that we had, the regularization term. So we can have L2 norm, L1 norm, different norms. Here I'm analyzing L2 norm, regularize it. Okay. So did they understand everything here? That we found the solution of J minimizer of J tilde, which is the regularized cost, and we saw that it makes sense because when we set alpha to 0, when the regularization term disappears, the minimizer of J tilde becomes the minimizer of J as expected. Okay, so now let's apply eigenvalue decomposition on the Hessian. Can we do that? Right. Yes, because Hessian is symmetric and also square matrix. And so this, we can set H is U delta U transpose, where U is the matrix of eigenvectors, and lambda, I think it's lambda. Lambda is the eigenvalues. So now let's replace in our solution X dagger, let's replace H with its eigenvalue decomposition. If we do that, so we'll have this inverse, therefore it becomes this inverse plus this inverse, right? By the way, no, before that, sorry. So we have this term inverse, right? Now, do you agree that U transpose is identity, right? Because U is the matrix of eigenvectors and it is an orthogonal matrix. And I haven't truncated that. So U transpose is identity. I can put it here. I can, because it will be equivalent to alpha I, right? And then why am I doing that? Because I want to, here I have U. I also want to have U here, so I can left factor out, right? So this is the reason. Now, do you agree that I can bring this alpha I in between, because alpha is a scalar, and I you don't just ignore this I, and there is an I in between, right? Because I doesn't do anything in matrix multiplication. So I can have this, and then now I have U at the left side of both terms. I can left factor out U. Also, I have U transpose on the right hand side of the term, so I can right factor out U transpose. Therefore, I will have this in the middle. Okay. Now I apply inverse onto the elements of these parentheses. So we know that similar to transpose, inverse also reverses the order of matrices when we have matrix multiplication. So we'll have U transpose inverse. What is U transpose inverse? U is an orthogonal matrix, right? Therefore, U transpose equals U inverse. So U transpose inverse is U inverse inverse. So it's U. So it's U. Then this term inverse, then U inverse, right? Then the rest of the terms are here, right? Interestingly, in the middle, we have U inverse U, which is identity, right? So it goes away and it simplifies to this. Agreed? Yeah, sure. Hi. Now, what were we saying? Okay, what are we doing here? Can you tell me? So what is U transpose X star? It's like, do you agree that we are projecting X star onto the column space of U? But if we haven't truncated U, it means that we aren't projecting onto a subspace. We are just rotating in the same space. Do you agree? So U transpose X star means that I'm rotating it. And let's ignore this term in the middle. If it was U transpose X star, if it was U transpose X star, what would it mean? It means that rotate it in the space and rotate it back. Because we know that according to the preliminaries, U reconstructs it back, right? And as I haven't truncated U, I haven't projected onto the column space. I'm just rotating in the same space. So simply, U transpose X star means rotate it and rotate it back. Don't do anything. However, now I have a pain in the neck term here in the middle. So it means that rotate it, do some transformation, and then rotate it back. Okay? But it won't be at the same place as before because I have this term. Okay? And that's exactly what regularization does, right? Okay, so we had this. Again, if we set alpha to 0, this goes away, this simplifies, so we'll have lambda inverse lambda, which is identity, then we'll have U transpose X star, and we know that U transpose equals U inverse because U is orthogonal, and as it is not truncated, it becomes identity, so X dagger reduces to X star as expected, because if we set alpha to 0, we won't have any regularization term. Now, what if alpha is not 0? Let's analyze that, okay? What if we have the regularization term? So let's analyze this. What is this? This is exactly the term that we have in the solution here, right? Let's analyze this term. What is this? If you consider it element-wise, you will have this. Why? Because lambda is diagonal. Why? Because lambda was the matrix of eigenvalues of the Hessian. Identity matrix is also diagonal. Okay, we know that the inverse of a diagonal. So by the way, lambda plus alpha I is also diagonal, right? We know that according to linear algebra, what is the inverse of a diagonal matrix? It's very simple. It's just the reciprocal of the elements of the diagonal. So when you have a diagonal matrix, the inverse of it is just inverse of elements in the diagonal, okay? Therefore, inverse of a diagonal matrix is also diagonal. So a diagonal matrix times a diagonal matrix is also diagonal. Therefore, we only have diagonal elements. And these diagonal elements are these. Lambda 1 over lambda 1 plus alpha according to this. Just consider it element-wise. And lambda 2 over lambda 2 plus alpha until lambda d plus over lambda d plus alpha, right? Now let's analyze it. It's very interesting. Two cases might happen. Either consider one of the elements, so lambda j, right? J goes from 1 to d. If either lambda j is much greater than alpha, or lambda j is much less than alpha. Let's consider. When lambda j is much greater than alpha, what happens to lambda j over lambda j plus alpha? It becomes almost 1, right? Limits this term where lambda j goes to is much greater than alpha. Then it goes to 1. Then what happens in this case? It means that at least for that element, it becomes 1 if all of the elements, their lambdas are much greater than alpha, then this matrix becomes identity matrix. Almost. Agree? Then what happens? In this here, if this becomes identity matrix, what happens? X dagger becomes U transpose X star. We haven't truncated U, therefore it just rotates and rotates it back, and X dagger becomes X star. Exactly X star, right? Because I'm not projecting onto a subspace. Now, the other way around. When lambda j is much less than alpha, then lambda j over lambda j plus alpha becomes almost 0. So all elements are like that. Then it becomes a 0 matrix, right? Now in the solution, put this 0, set it to 0. What happens? X dagger becomes 0, right? So in other words, for elements where lambda j is much greater than alpha, the solution of regularized optimization is the same as you don't have any regularization for those elements, for those directions, right? But for those directions or elements, or for those dimensionalities where lambda j is much less than alpha, then the solution of regularized optimization shrinks to 0. Shrinks, reduces, right? Did you understand the meaning? So what?
Here and why we need it.
No. So we solved that optimization problem. So we minimized. Remember what we did? We had this minimization, right? This regularized minimization, and we solved it, and we ended up in equation 27, right? And we also simplified and worked out the equation 27, and we ended up in equation 29. So this is the solution to for the regularized optimization with L2 norm regularization. Now we are analyzing that. So you are saying that it has U transpose X star. If we didn't have this something appears because of regularization. If we don't have this something, X dagger becomes X star because I haven't truncated U. So it just means that rotates X star in the same space and rotate it back. It will be exactly where it was. The reconstruction error is 0 here because I haven't truncated U, right? So now we are analyzing that. We are analyzing the effect of regularization term by this. So we have two cases. For some dimensionalities, lambda j is much greater than alpha. What was alpha? The weight or the regularization parameter, the weight for regularization, right? We said when lambda j is much greater than alpha, what was lambda j? The eigenvalue of Hessian, right? So when lambda j is much greater than alpha, it means that that direction is very important for me, right? Because that's the eigenvalue of the Hessian of j, of the actual cost. That direction is important for me. Then in this case, it means that ignore the regularization term, because lambda j over lambda j plus alpha is almost 1, right? And if you set 1 here, it becomes U transpose X star. So it becomes X star, which is the solution of the minimization of actual cost. Okay. But when lambda j is much less than alpha, it means that the eigenvalue of the Hessian at that direction is not that much important with respect to alpha, with respect to the regularization term, then shrink it. In summary, for those directions where my actual cost is important, ignore the regularization term. Consider my actual cost. For those directions where my actual cost is not that much important, consider the regularization term, so shrink that direction. Understood? What? It can be any cost, j. So here we said it is j, right? J. It can be any cost. It can be mean squared error. It can be cross entropy. It can be anything, right? J plus alpha over 2, this regularization term.
You rotate the variable to a different dimension, or
So I'm saying that the solution of the regularization term, you can see it as U, as exactly this, as this. And then if you consider it element-wise, for those directions where the actual cost is important, it's like that you're rotating that direction and rotating it back. So you don't do anything on that. So you ignore the regularization term. Okay. Did you understand the beauty of what regularization term is doing when we have L2 normative? Okay. This that we had lambda j over lambda j plus alpha. Summation of this over the dimensions, they also call it effective number of parameters or degree of freedom. It was named by Hasty and Tifshirani at Stanford in their very well-known book, Elements of Statistical Learning. Okay, so, and also you can consider this term as a shrinkage factor because it shrinks, right? Okay, now we go to L1 norm regularization, which is much more interesting. Okay, so as we talked about it, sparsity is very useful, right? According to Bettinan's sparsity principle and also Occam's razor. Agree? So let's consider this X, right? D-dimensional X. For having a sparsity, we can use subset selection for regularization. As a regularization term, I can use subset selection. What is subset selection? This is subset selection. So norm 0. We set P to 0. But is it a norm? No, it is not a norm. Okay. Therefore, when we want to refer to it, we say double quote L0 norm, right? Here. Double quote L0. So it's because it's not norm. It doesn't satisfy the properties of the norm. Recall preliminaries. Okay. But this is its definition. So we say summation of, what is this? The indicator function for whether xj, that element, is 0 or not. So simply this summation is counting how many how many non-zero elements do I have? Okay, for counting how many. So assume, for example, X is 5-dimensional and it has 3 zeros and 2 non-zero elements. So subset selection of X will be 2, right? Because it has 2 non-zero elements and 3 zeros. So if I regularize that, I'm minimizing that, right? What does it mean? Minimize the number of non-zero elements. So try to make X sparse. Try your best so X becomes as zero as possible, as many zero as possible, right? As you see, it became discrete, counting number of zero elements. So of course, it's not smooth, it's not convex, it's a pain in the neck, right? It's a big problem because it became discrete optimization. We should make it continuous again. So the convex relaxation of this subset selection is L1 norm. Okay. So L1 norm, if you consider, because these norms, you can see them as cones in the space. Okay. So L1 norm has some cone. Imagine, you should imagine. This is a cone of L1 norm. And we know L1 norm is a norm, and that is also convex, okay? L0 norm is here, outside of it. If you project L0 norm to L1 norm cone, to convexity norm. Sorry, let it be convexity norm. Convexity space, sorry. The closest point in the convexity space to L0 norm is L1 norm. You cannot find any norm closer to L0 norm. Did you understand? Among the norms. So assume you have a lot of candidate norms. Do you agree? You have L1 norm, you have L2 norm, you have L1.5 norm, you have L1.7 norm, right? Sweep P, you have LP norm, right? Which one is the closest to L0 norm? It can be proved mathematically. That is L1 norm. For proof, you can see this paper. reference 16. Okay, so that is the reason that I told you, whenever you hear L1 norm regularization, you should think of sparsity. Okay, so this is called Lasso, also Lasso regularization. I think it was named by Tibshirani. Lasso is short for least absolute shrinkage and selection operator. I know it's very long, so Tibshirani named it Lasso. Okay, and you will understand why he named it least absolute shrinkage and selection operator. Why? I think you already know what shrinkage means, because L2 norm also shrinks, right? And L1 norm also shrinks. But L1 norm does something additional. And it selects, similar to subset selection. What does it mean by selecting? It means that it selects some of the dimensions and sets the other ones to 0. Okay? We'll see that.
One norm is closer to absolute norm.
So it is in mathematics, by the way, call me Benjamin, don't need to call me the professor of this. Okay, so in mathematics, when I have some problem, usually when the problems are hard, we can relax them. You hear this a lot. They say, let's relax a problem. For example, when they have integer linear programming, they solve it as a tree, and at each node of the tree, they relax the problem to linear programming, which becomes continuous. So they relax a discrete problem to a continuous problem. This relaxation also sometimes is called reduction. Let's reduce that to some relaxation or reduction. Here, when we want to relax the subset selection, it becomes L1. And what do I mean by relaxation? I want this to become a norm to satisfy the properties of the norm. But which norm is the closest one? Has the least amount of error compared to subset selection? That's the L1 norm. And it has a mathematical proof. Okay. So different methods exist for solving L1 norm and L1 norm optimization. For more information, you can see my lecture on YouTube about I think it was non-smooth optimization. I have a lecture on in my optimization techniques course. Okay, but at least two of them are soft thresholding and coordinate descent. I have explained all of them in that lecture, but we'll go through that a little bit here. So the idea now, let's consider the coordinate descent. What is coordinate descent? Coordinate descent says that let's optimize our optimization problem with respect to elements, element-wise. Rather than the whole vector, let's consider the vector element-wise and optimize that cost with respect to elements. Hence the name coordinate descent, right? Okay, so with respect to coordinates, with respect to elements, with respect to dimensions or features. Why is it useful for L1 norm? Recall preliminaries. When you set dimensionality to 1 in L1 norm, every dimension becomes an absolute value, right? So when the dimensionality is 1, L1 norm reduces to absolute value. Okay. So we can deal with absolute value, but we can't deal with L1 norm. L1 norm is a monster. Let's make it a mini monster. Although absolute value is still a mini monster because it's not as smooth at the origin, but at least we can handle mini monster, right? Okay, so that's the reason. And by the way, its idea is similar to Gibbs sampling. Have you heard of Gibbs sampling in statistics? No? So Gibbs sample in statistics, when we have a probability distribution, right, which is a joint distribution of a lot of variables, it's maybe hard to draw a sample from this joint distribution. It might be very complicated. Then we say, let's consider one of the variables and condition it on all other variables. What do I mean by conditioning? Assume all other variables are not random, are fixed, and let one of the elements to be random. Then sample from that. Then go to the next element and assume the other ones are fixed, then sample from that. Then do this iteratively, and then come back again and do this element-wise iteratively until you converge. You will converge. Okay, that's called heap sampling. After convergence, it's like the sampled points is like that you have sampled from the joint distribution. Okay, it's very interesting. So here, consider this regularized cost. Now I'm replacing J with J hat, which was the Taylor series expansion at X star. Again, according to what we discussed minutes ago, it is this, right? And where X star is the minimizer of J, right? The actual cost. But here now I have L1 norm. So I'm using coordinate descent. Therefore, I don't consider the whole X. I consider xj, the jth element of X, right? And J, I sweep it from 1 to D, right? So only considering xj, what happens? So this becomes the J hat of xj plus alpha absolute value of xj, right? L1 norm of X became absolute value of X. Don't you agree? What was L1 norm of X? It was summation of absolute values of xj. Don't you agree? Recall preliminaries. So only if you consider only one of the elements, the summation goes away, right? So you have this. You understand why the summation goes away, or you just say you're accepting. Understand why the summation goes away. Because this, what is this? It's absolute value of x1 plus absolute value of x2 plus absolute value of x3 until absolute value of xd. In coordinate descent, I'm assuming all of them are constant. Only I'm optimizing with respect to xj. So absolute value of x1 becomes constant. Absolute value of x2 becomes constant. Only absolute value of xj is important. Okay, so now I have this. Again, if I consider this element-wise for xj, I will have this. Now, this is scalar, so this quadratic form became a square form, right? Because it's scalar. Now I have this and some other elements which we don't care because of the Taylor series expansion. So now let's take derivative, set it to 0, because we want to minimize this, right? With respect to xj. Set it to, so take derivative with respect to xj, set it to 0. So this becomes 0. Why? Because it's a constant with respect to xj. This is quadratic with respect to xj, becomes this. Also, what is the derivative of x, absolute value of xj? No, the derivative. So I need a space to draw. Just give me, let me add a new page. This is absolute value of xj, right? So derivative of this part, what is it? 1, right? Derivative is a slope, right? So 1. Derivative of this part is -1. For now, disregard the 0, okay? For now. What is this? Sine function, right? So derivative of absolute value is sine. So sine of xj, okay? Set it to 0. And what happens? Rearrange the terms. Rearrange the term. You will get this, right? Therefore, when xj is positive, we have this. It simplifies to this. When xj is negative, it simplifies to this, right? This is called soft thresholding function. Whenever you work with L1 norm, optimization of L1 norm, you hear soft thresholding. Okay. So when we draw soft thresholding, it is like this. It's a plot like this. So what does it mean? When xj is greater than 0, what is this? It's a line. So with respect to xj star, I mean, it's a line where its intercept here is alpha plus over xj, right? Do you agree? What is this then? When xj is negative, it's a line where the intercept is minus alpha over hj. So let's connect these two. So these two lines here, right? That's why I said for now, disregard the zero. We can figure out the zero here. What happened with the zero? Okay. Now, this is the relation between xj dagger and xj star. What was xj star? The minimizer of actual cost. What was xj dagger? The minimizer of regularized cost with L1 norm. Can you analyze this? So let's consider these two cases. When xj star is less here, when in this plot, when xj star is less than so xj star absolute value is less than alpha over hj. What does it mean? I'm in this region. Do you agree? Right? What happens? What happens to xj dagger? In this region, what is xj dagger? It's zero, right? What does it mean? When my xj star is less than some threshold, and this threshold is alpha over hj here, set it to zero. Push it to zero completely. Make it zero, make it a sparse. That's direction. So this is element-wise, right? Jth element. We have these d times for d elements, right? For each element, when that direction is not that much important, push it to zero. Set it zero. Otherwise, shrink it. It is in these regions, it is shrinking. It is shrinking, but not setting to zero. So now compare it to L2 norm regularization. In L2 norm regularization, we only had shrinkage. We only shrinked to close to zero. Here, in addition to shrinkage, for some things which are too small, we make them zero. Exactly. So L2 norm regularization might give you this, might shrink it to 0.0001. But L1 norm regularization makes that zero exactly. That's the reason L2 norm regularization is not sparse. It has some trees in the forest, but the trees might be very small. L1 norm regularization completely removes those trees. Right? Interesting. Now, let's see this figure. This figure, its credit is for Tipshirani in his paper for Lasso. So when he proposed Lasso regularization or Lasso regression, he drew this. It's a very interesting analysis. What is that? So you can see, by the way, it was published in 1996, reference 8. So what is that? It says consider figure A and figure B. What is this? This is the unit ball for L2 norm. If you don't know what unit ball is, don't worry. It means that whenever the norm is 1 and less than 1. Okay. So by the way, you know the difference of ball and sphere in mathematics? Do you know that in algebraic topology and these things? Okay. So in topology, when we say sphere, consider a ball or a sphere, whatever we know in this world. If you only consider its skin and not its interior, in mathematics, they call it a sphere. So we might have hypersphere, right? So a sphere in 2D is a circle. Sphere in 3D is just a ball, but only its skin. We might have hypersphere in higher dimensions, right? Whenever we also, in addition to the skin, we also consider its interior, they call it ball. Okay, ball. So ball in 2D is a circle with its inside. In 3D is a sphere with its inside, and we also might have hyperballs, right? That's a difference you should know. So now here, when we say unit ball of the norm, it means that wherever the norm is 1 and also it's inside and also less than 1. So when norm is less than or equal to 1, that's the unit ball of the norm. This is the unit ball of L2 norm. This is the unit ball of L1 norm. Okay. Now, what does this mean? This is the actual cost. If I only consider the actual cost and its minimization becomes what? Do you know what this means, by the way? I have explained that to you beforehand. So at every line, the cost value is the same. I'm looking at the cost from above. This is a 2D. So I have two variables, and I am looking at the cost from above. If I only have minimization of J, what happens? Ignore this. Ignore this. I don't have no norm, right? Minimize. This is a ball, a bowl coming up, right? A bowl, quadratic. What is the minimum of the bowl? It's below. Exactly here. So X, X star was the minimizer of the bowl, the actual cost. So this is X star 1, X star 2. Agreed? Now let's add the regularization term. Okay. Now, for a second, forget the actual cost, and only consider the norm, minimization of norm. What do I mean? Minimize L2 norm, squared L2 norm of X. But I don't have any J. So what should I do? Completely forget this cost. This is also like a ball, right? Coming up, but this ball is the same from all directions, right? So it's not like an oval. Then this ball, looking at from above, where is its minimum? It's below. Where is it below? Exactly 0, right? Agree? And why don't you challenge me? Ask me, why have I put this unit ball on the origin? Why? Because L2 norm of X equals 0 should be 0, right? So I have put it on the origin. So minimization of only norm will be here. So in summary, minimization of only actual cost is here. Minimization of only regularization term is here. So the minimization of their linear combination should be somewhere in between, right? Somewhere in between, depending on the alpha. When you increase alpha, you give more weight to the regularization term, right? Now, these two costs intersect somewhere. The solution will be at that intersection, right? So they will intersect, for example, here. So it gives us X1 dagger and X2 dagger. Did you understand it? Okay. Now let's compare it to the L1 norm regularization. What happens? It becomes like this. So I should see where they intersect, right? Where do they intersect? With high probability, probably it will intersect at one of the edges of this, because unit ball of L1 norm is like a diamond. Unit ball of L2 norm is like a ball, a sphere. Okay. So unit ball of L1 norm has sharp edges. Okay. Therefore, do you agree with me that when I have sharp edges, I'm bringing a balloon close to it? With high probability, the balloon will touch the sharp edge with sharp vertices, right? And this probability increases if we increase the dimensionality. Why? Because here it is in 2D, so I have 1, 2, 3, 4 corners. In 3D, I will have 1, 2, 3. So it becomes like 2 pyramids back to back. So 1, 2, 3, 4, 5, 6 corners. Increase the dimensionality. You can't visualize it, you need to imagine it. It will have a lot of sharp edges. When you bring the balloon next to it, it will probably touch some of the edges, sharp edges. And interestingly, when it touches the sharp corner, many of the other elements become exactly 0. Here, when it touches here, the solution will be here, and its x1 is 0, right? Now compare these two, L2 norm and L1 norm. Can you see the difference? In L2 norm, here, X1 dagger, here, X1 dagger is a small, maybe 0.0001, but it's not 0. In L1 norm, it's exactly 0. That's the reason that L1 norm makes it sparse. Did you see the beautiful analysis by Tibshirani? Right?
In what case we need sparse regularization?
So whenever, first off, not always, usually according to the Bettina sparsity principle, sparse solution is better. But sometimes you actually need a sparsity. For example, maybe you don't, space is important for you because when you store a sparse vector, you don't need to store all of the zeros. You only store the elements, the coordinates where we have non-zero elements, right? So when space is important, for example, a sparse solution might be good. But anyway, in machine learning, whenever they propose an algorithm, it is possible to propose a sparse version of that too. And then you can compare which one works better. Okay. So acknowledgement, some slides are inspired by the textbook of Hasty, Tibshirani, and Friedman, The Elements of Statistical Learning, Data Mining, Inference, and Prediction by Springer. And another textbook suitable for sparsity is again by Tibshirani and Hasty and Wainwright, recently published in 2015. Its name is Statistical Learning with Sparsity, the Lasso and Generalizations. Not discrete. It puts a lot of zeros in the solution. So consider a forest. When you have short forest, the trees are just shrinked. But when you have a flat ground, then it's completely sparse. When you have in your vector and matrix, you have a lot of zeros, it is sparse. So some slides are inspired by some of the teachings of Professor Ali Qudsi at the University of Waterloo. And some yes, he has explained this part very well. Also, some slides are inspired by lectures of Professor Hoda Mohammed-Zadeh at Sharif University of Technology. She was my supervisor in master's. Some slides are based on our tutorial paper. Also, I believe this is a good tutorial paper. Feel free to read that. The theory behind overfitting, cross-validation, regularization, bagging, and boosting tutorial. Okay, so these are the references. Okay, let's continue with the next thing. Now we enter regression, okay? Linear regression. Basics are covered. Now we enter the basic algorithms for regression, for classification, and this. Linear regression. So for regression, we will cover regular linear regression and regularized linear regression. Again, we use L2 norm regularization and L1 norm. The linear regression with L2 norm regularization is called ridge regression. Linear regression with L1 norm regularization is called lasso regression. We'll cover. Okay. Consider a data set x1 to xn, right? Where each point is a d-dimensional vector. Okay. We have some labels too, y1 to yn, where each label is a p-dimensional vector. It might be a bit weird for you because usually you might have heard that the labels are scalars, but this is more general. If you set p to 1, then the labels are scalars, right? So here I'm more general. I'm assuming that the labels are also vectors. In real world, what does it mean? Assume I have a regression problem. So based on for example, coordinates, longitude, latitude, based on the pollution of the city, based on I don't know, the time of the year, and several other factors. I want to predict two things: the weather, and what do we say? The weather. So the temperature and whether, for example, it will rain or not. So two things, okay. Or let me give a better example. The temperature and what? Humidity, maybe. Temperature and humidity, okay? So my x's are the vectors of the pollution, the longitude, latitude, and these things. These are the features of x. The features of y, the labels are pollution. This is the temperature and humidity. So here, my labels are two-dimensional. I can have more. So based on several inputs, I can predict several outputs, right? And these outputs might be one output, doesn't matter. Okay. The labels are not necessarily discrete because it's a regression problem, right? It might be continuous, okay? Example, data can be the data of weather, temperature, longitude, latitude, etc. And the label can be pollution. Doesn't matter. Okay, this is an example. So we can consider a map, the learning map, right? F, which maps data to labels. Consider a map which gets the data and outputs the labels, right? So f of x, the outputs the labels but f of x plus some noise is the labels. Why? Because I don't completely trust my data set. What if when they were measuring the labels, there was some error, measurement error, or that person was lazy who was collecting the data and these things, right? So one might have noise. Therefore, I say y equals f of x plus some noise epsilon. And epsilon is also p-dimensional. So the dimensionality of epsilon should be the same as the dimensionality of labels. Because why? Because f gets a d-dimensional vector and outputs a p-dimensional vector, right? So in regression, we want to estimate this map, f, right? So in linear regression, we want to estimate this map by a line or a affine function. When I say, by the way, line, I mean hyperplane, right? So in 2D it's line, in 3D it's a plane, right? In 4D you need to imagine it, it's hyperplane. It's linear, but as I might have intercept, let's call it affine function, okay? So first, for now, consider that my labels are scalar for now. We will generalize it. So if p is 1, then f of x will become a scalar, right? F of x is a scalar. So can I write it in this way? What is this? It's a linear function, right? With the parameters beta 0, beta 1 to beta d. Do you agree that this is a linear function of x? Okay. And here beta 1 to beta d can tell me the slope of this line, and beta 0 is for bias. Because in my data, in my actual data, I might have bias. I need to capture that. Okay. And xj is the jth element of x, right? And beta 0 to beta d are the learnable parameters, the parameters which I want to learn. Yes. Can you be louder? Noise and bias. So noise is because of the errors that I might have in my data. But bias is that actually, for example, as I told you, assume that the example of getting the pollution, the longitude, latitude, and outputting predicting the temperature and humidity. Okay. So longitude and latitude in my data set. So I have a lot of longitudes and latitudes. Is the mean of these 0? No, not necessarily. I need to capture that. So I need a bias to capture the mean of longitude. A bias for capturing the mean of latitude, a bias for the mean of other things, such as pollution. Here, so I'm saying that you need to take into account the bias, otherwise you can't capture. So whatever you find, you learn, its mean will be 0, although your data it might be somewhere else in the space, right? Yeah, exactly. So you need to take into account the mean of the features, and this beta 0 handles that. Otherwise, as I said, for example, it will be like, for example, this is your data. You need to fit something like this, right? You will fit something like this, passing through 0, because its intercept is 0. See, it's not wrong. It's wrong, right? Okay. So
Bias of the data set, why don't we add actual inside bracket? I mean,
So, may I say something? I said something wrong. It's not for capturing the mean of inputs. It's for capturing the mean of outputs. Sorry, outputs. Okay, the labels. Okay, labels, because it's f of x is beta 0 plus something. So it's the mean of the output. Here also in the plot that I showed you, it's the mean of the output, y x, right? Okay. So one way to do this estimation is what? Let's minimize the least squares error or mean squared error between the labels and the estimated outputs. Do you agree? I want my estimated labels to be as close as possible to the actual labels that I have for training data. So let's minimize the mean squared error between them. So yi, which is the actual label, minus f of xi, which is the predicted label. This is the error between them. I square them because I don't care for the sign of the error. And then I sum over all of the points, right? So let's minimize with respect to beta 0 until beta d. Therefore, I have d plus 1 optimization parameters, optimization variables. And now let's replace f of xi with equation 2. Okay. So I will have this. And here, xij is the jth element of xi. Okay. So it's a scalar. Xij is a scalar. Xi is the ith data point, ith vector. Xij is the jth element of xi. Right? Okay. Now I want to write this in matrix form. We do that a lot in machine learning. Rather than elements-wise, let's do it in matrix form. So how can we do that? So I put all of the betas next to each other in a vector. So it's a column vector, right? So I denoted by beta, bold beta. It's d plus 1 dimensional, right? Also, I put all of my data points row-wise here. Except in regression, in other parts of the machine learning, usually we put data points column-wise. Okay, usually. In regression by convention, they usually put them row-wise. You still can put them column-wise, but the last formula that you derive will be different from the well-known formula that you have for regression in the literature. Okay. The well-known formula in the literature assumes that your data points are row-wise. Okay, for now. So here is exactly like scikit-learn. We put them row-wise, but at the start, I put 1. Why? For bias. And why do I put 1 at the start, not at the end? Because beta 0 was for the bias, which is here, right? Beta 0 is at the start. If you consider the last beta for bias, then you should put 1 at the end. Agreed? Okay. Then also let's put all of the labels. Sorry, it should be y1. I apologize. y1 to yn next to each other in a vector. It will be n dimensional, right? Do you agree that this equation 3 can be written as equation 4. Let's consider that. So y minus, what is xb? X beta. This is x beta. If you consider it element-wise, it becomes this summation. Actually, this summation. It has beta 0 in it because beta has beta 0 in it, right? So I can write this as x beta. Why? Because what is the dimensionality of x, by the way? It's n by n rows, because I have n data points. And d plus 1 columns. Why? Because each of the data points is d-dimensional, also adding 1 for bias. So n rows and d plus 1 columns. Therefore, this is n by d plus 1. What is beta? d plus 1 by 1. Right? D plus 1 dimensional column vector. So x beta is correct. Beta x is wrong. Right? According to matrix multiplication. Also, what is y? It's n by 1. What is x beta? The whole thing together. So n by d plus 1 by 1. So it is n by 1. So we can compare an n by 1 vector with an n11 vector. So that is correct. Okay. So y minus x beta is the error between the actual label and the predicted labels, but we need squared L2 norm because of this. So this is this squared, we have it in L2 norm, right? However, the L2 norm itself has a square root. Here we don't have the square root, so we should have a squared L2 norm. Agreed? Okay. Now my optimization variable becomes the vector beta rather than element y, becomes a vector beta. The cost function here, let's simplify. Recall preliminaries. Okay. So everything, a squared L2 norm of something is that thing transpose that thing, right? So that thing transpose that thing. And transpose can be applied on the elements when we have a summation. So it becomes y transpose and this term transpose, but this is multiplication and transpose reverses the order in matrix multiplication. So I'll have beta transpose x transpose and also this. Now let's multiply the terms together. How many terms do I have? 2 by 2. So I'll have 4 terms. So this by this by this, then this by this, then this by this. So it becomes y transpose y minus y transpose x beta minus beta transpose x transpose y plus beta transpose x transpose x beta. Okay. We have seen these things in high school, but for scalars. Okay. So let's take derivative with respect to our optimization variable, which is beta. Right? So this thing is a scalar. Do you agree? Squared L2 norm is a scalar. Derivative of a scalar with respect to a d plus 1 dimensional vector must be a d plus 1 dimensional vector. Okay, let's calculate it. What is the derivative of this with respect to beta? This is constant, goes away. What about this one? This is linear with respect to beta. So it becomes minus either y transpose x or x transpose y. Which one? According to the technique that I told you. You can see that. Let's see it for a second. This is d plus 1 by 1. This must be 1 by d plus 1, right? And I know that the derivative of this scalar with respect to beta must be a d plus 1 dimensional vector. So d plus 1 by 1. Y transpose x is 1 by d plus 1. So I should transpose it. So I should put x transpose y, which is a column vector, because y transpose x is a row vector. Did you understand? I think you didn't understand, right? Did you understand? You understood?
Yeah.
Okay, that's. Let me know if you didn't understand. Okay, so here, what about this? It's linear with respect to beta or beta transpose. So the solution, by the way, this is a small y, sorry. The solution is either x transpose y or y transpose x. Again, according to that analysis, we can find out that it's x transpose y. And this one is quadratic with respect to beta. Therefore, it must be 2 X transpose X beta, right? Now set it to 0, and this 0 is a vector 0 vector, right? Rearrange the terms, you will have these two twos cancel each other. This is a pain in the neck. X transpose X is a pain in the neck. What should we do? Multiply by its inverse, right? Left multiply the sides by X transpose X inverse. So the left hand side goes away, and we'll have this times this. So beta became equal to X transpose X inverse X transpose Y. This is the most famous formula for linear regression, right? And so we wanted to find beta, right? We just found it. And interestingly, it was closed form solution. So we don't need to optimize it iteratively. We don't need gradient descent. If we couldn't find beta in a closed form solution, we had to iteratively optimize it, right? Now, but we use the high school rule, first order optimality condition, and we found the solution in closed form solution. Okay, so training is finished. We found beta in training. Now test phase. Some X comes, right? And this X, by the way, we might have several data points. We might have several test data points, right? Do you agree that I can stack them and get together to make a test data set, right? How can I prepare the test data set? I have to exactly prepare the test data set exactly the same way that I prepared the train data set. How did I prepare the train data set? Here. I put them row-wise. I put 1 at the start for bias. So it became n rows and d plus 1 columns. Now in the test phase, assume I have q data points, q test points. I put them row-wise with 1 as the first column. So we'll have q rows and d plus 1 columns, right? I denote it by x. Now you tell me, how can I predict the labels of the test data set? What formula should I use? I say that I claim that it is X beta, but can you tell me why my claim is correct? Yes, it's linear regression, but can you explain it more clearly why X beta is correct here, the correct formula? No, I agree. So you're saying that this is linear with respect to X, and it is linear regression. But I'm saying that why is X beta correct? Shouldn't I use X beta plus some other thing, or why shouldn't I use, I don't know. First off, beta X is wrong in terms of matrix multiplication. Why can't I use X plus beta? Why this formula? The reason is that, what did we minimize? Y minus X beta. What was X beta? The predicted labels. What was Y? The actual labels. The formula says that here. X beta is the predicted labels. So yes, let's use that in the test phase as well. Right? Did you understand? X beta is the predicted labels. So I use that. And beta, I replace beta with equation 5. So this is beta. So my Y, which was X beta, becomes X times X transpose X inverse X transpose Y. This is also very famous. Okay. Again, let me emphasize that this X can be the data set of anything. It can be the training data set again. So after training, you can predict the labels of training data set again, right? In scikit-learn, that's called fit transform. You fit it once, and then you transform the training data again. Or this X can be a test data set, right? It can be anything. but you should prepare it as we did here for the training data. So in machine learning, this is a general rule. Whatever you do on the training data, you have to do it on the test data too. If you do some pre-processing on the training data, you have to do it on the test data too, right?
Why in most machine learning analyze we use vector in column wise?
Because so the question is why we use vectors in column-wise format in most of the machine learning, because it makes our calculations easier. That's the reason. I believe it's no, it makes it harder. Row-wise is easier for coding, for Python, scikit-learn, and this. In most of the libraries, they consider them row-wise, similar to how it is stored in CSV files, Excel files. But usually in linear algebra, machine learning, we consider them column-wise because that's easier. But in linear regression, we consider them row-wise. Again, it's not a rule. You can also consider it column-wise, but you will not end up with equation 5. Okay, it will be another. It will be some other thing, such as it will be, for example, I think x transpose inverse, something like that. It's not the well-known formula. Okay. In a more general form now, if P is not 1, now let's generalize it to the case where the dimensionality of label is more than 1, right? So each of the yi's or yj will be a vector. So we can stack them row-wise now. Again, the labels also should be stacked row-wise. Therefore, I will have an n by p matrix y with n rows and p columns, because each label has p dimensions. And now my beta becomes a matrix. My beta was a vector, right? Now my beta becomes a matrix where I'm putting beta 0, beta 1, until beta d row-wise. Why? So these are column vectors, right? But I'm transposing them. So these are row-wise. So I will have d plus 1 betas, each of which is p-dimensional. D plus 1 rows and p columns. My B became a matrix. Agreed? Now, if I want to form my optimization problem, it will become this. Y minus xp. It's very similar to what we had in vector form for scalar labels. Y was a vector minus x beta. X beta was also vector, because why is y a vector? Because I have n labels, each of which is a scalar. So it becomes a vector. However, here, my y is a matrix because I have n points, n labels, each of which is p-dimensional. So it's a matrix, but the format will be similar to equation 4. Rather than this, y becomes a matrix and beta also becomes a matrix B. So it becomes like this. Y minus xb. Let's see if the dimensionalities match. B is d plus 1 by p. X is n, I'm right? Yes, n by d plus 1. Y is n by p. xb becomes n by p, so they match. I'm comparing an n by p matrix with another n by p matrix, right? But this difference is also a matrix, right? Should I use L2 norm? No, this is a matrix now. I should use Frobenius norm. Recall preliminaries. Frobenius norm, but a squared Frobenius norm, because a squared Frobenius norm is convex. Also, I don't have a square root here, right? Minimize that. So let's simplify the cost function. Again, according to the preliminaries, squared Frobenius norm is quadratic. Anything, something Frobenius norm squared is that thing transpose that thing, but now I need trace also to make it a scalar. Trace of that thing transpose that thing, right? So now apply transpose on the elements. So I will have y transpose xb transpose, reverses the order, b transpose x transpose. Now I have, again, similar to before, I have 4 terms. This, let's multiply the terms together. also consider the fact that trace is a linear operator. So I can apply the trace on the elements, right? So this, the first term, minus the trace of this, minus trace of this, plus trace of this. Okay. This is a scalar. We want to minimize that with respect to, what is my optimization variable here? The matrix B now, right? So take derivative of cost with respect to B. Derivative of a scalar with respect to a matrix is a matrix. Recall preliminaries. So what happens? What is this? It's a constant with respect to B, goes away. What is this? It's linear with respect to B, becomes X transpose Y. Why not Y transpose X? Use the analysis that I told you. Okay, check the dimensionalities. This also is linear with respect to B or B transpose. And if we check the dimensionalities, its derivative is X transpose Y. This is quadratic with respect to B. Its derivative is this. Set it to 0. Rearrange the terms. You will have these. These two 2's cancel each other. This is a pain in the neck. Left multiply the sides by this inverse. You will get this. Very similar to the previous, but now Y is a matrix, so B is also matrix, right? In the test phase, again, I prepare my X the same way that I prepared my X for training data, and my prediction is XB. The previous one was X beta. This is XB, right? And my output, my predicted output will be whatever number of points that I had in the test phase times what? I mean, the number of rows is the number of test data points. The number of columns in Y will be the dimensionality of labels, right? Simple linear regression was over. Okay. By the way, linear regression fits a line, or as I told you, for example, if I have this, if I apply a non-linear regressor, for example, an example of non-linear regressor is deep neural network. If you use deep neural network for regression, it will be non-linear, and it will fit. It might fit like something like this. Okay, but if you apply linear regression on it, it will fit a line to it. Okay, of course you have some errors, right? Well, that's fine. Of course you have some errors and you want to minimize these errors. So because this is also a line, this is also a line, which one has the minimum error for prediction? This one, right? By the way, what do I mean by fitting a line like this? Let me clarify this. For example, I do this. What do I mean? I mean, for this X, my actual label was here, my actual label. But what I predict is here, Y hat. As you see, there is a difference between Y and Y hat. And we were minimizing this difference for training data. Now let's consider ridge regression. We add L2 norm regularization term as a penalty, right? On the size of learnable parameters. So we want to shrink them, penalize them as a regularization term. So now again, consider that for now, consider we have one scalar label. So P is 1. What happens? What happens? I have, what is this? This is exactly what we had in linear regression. The actual cost. Now I add a regularization term, which is a squared L2 norm, right? Because L2 norm has a square root, but it is a squared L2 norm, so square root goes away. And this lambda is a regularization term, regularization parameter. And it must be greater than 0. Why? Because I'm minimizing this. If lambda is negative, this minimization becomes maximization. Okay. So this part, if we write it in matrix form, it becomes this, right? Exactly what we had in linear regression. The difference is this. What is this? Is lambda times squared L2 norm of the vector beta. The vector beta. So we want to minimize it with respect to beta. So the only term which is added here is this. Now let's simplify the cost function, because we want to optimize it, right? So this is simplified to this as before. This is simplified to this as before. The only thing is this. Here is simplified to this because this is quadratic form. Okay, for you who are not here, just let me tell you very briefly. So here we are just adding an L2 norm regularization term. Okay, the difference with this compared to linear regression is just adding this regularization term. Now we are simplifying this cost. This is simplified to this, and the rest is as before. Okay. Why? Because of the analysis that we had minutes ago. Because we do you remember it shrinks beta. Why? We don't want beta to become too big. Beta was the optimization variable, right? I don't want it to blow up, to become too big. So I penalize it. What is this? You can see it as a squared length of beta, vector beta. So when I penalize the length of the beta, vector beta, it means that the elements of the beta should be small, shouldn't blow up. What? I can't hear you well. Yeah, the value of lambda, right? Yeah. Lambda shouldn't be negative. Lambda should be positive. Otherwise, my minimization of this, because you are minimizing this penalty, right? If lambda is negative, what happens? You're maximizing this penalty. Beta becomes infinite, right?
It is used to reduce the dimension of.
No, not dimension. The values of beta. The beta is a d plus one dimensional vector, right? It has several values, d plus one values, d plus one elements, each of which has some value. I don't want these values to blow up, and these values might be positive or negative. By blowing up, I mean I don't want them to become infinite or minus infinite or large, such as 100 minus 100. I want them to be small, right? By this regularization term.
The same meaning as the regularization in other machine.
Yes. So whenever we have various techniques for regularization, a lot of them. We analyze the regularization for in general. Also, we analyze it for as a penalty term. But almost all of the regularization techniques that you see in machine learning, you can analyze them as a penalty term in a cost. So whatever you do, you can mathematically analyze it that it's changing the cost somehow. Okay. For example, in deep learning course, I will cover it. You can see even early stopping as this. You can see dropout as this. You can see. So we have various techniques for regularization in deep learning, such as batch normalization, dropout, ReLU, weight decay. All of these can be seen as a penalty. Okay. So here we are regularizing by squared L2 norm, and we simplified it, and we ended up with this, right? Now what should we do? Take derivative with respect to optimization variables, right? Let's do that. So this, until here, we did it like exactly as in linear regression, right? This term is added. What is this? It is quadratic form with respect to beta, because it's beta transpose beta, right? By the way, it has some lambda here. Sorry. So it becomes 2 lambda beta. Agree? No. Okay. Now set it to 0. zero vector. So what happens? These two simplify to minus 2x transpose y. I bring them to the right hand side. It's this. The rest is at the left hand side. I can factor out 2 here. Also right factor out beta here. Agreed? So I'll have this. These two 2's cancel each other. Then this is a pain in the neck term. I left multiply the sides by its inverse. So I'll have this. Right? This is also a very famous formula. How is this equation, which is a solution of optimization problem, right? In ridge regression. How is it different from simple linear regression? It was, let's go back. What is the solution of simple linear regression? Equation 5. X transpose X inverse X transpose Y. Let's go back to where we were now. It became X transpose X plus lambda I inverse X transpose I. So this plus lambda I is added. Okay? As expected, because lambda was the weight for the regularization. If you set lambda to 0, it should become like simple linear regression as expected. Right? Okay. What is this plus lambda I doing? Let's analyze that. Can you tell me without reading the line? Okay. So X transpose X is a matrix, right? What was that beforehand? X transpose X inverse X transpose Y. It was better, right? In simple linear regression. Why no one told me what if X transpose X is singular? What do I mean by singular? It's not invertible. So a singular matrix is not invertible. A singular matrix, at least one of its eigenvalues is 0. It has one or several 0 eigenvalues. You can't invert it. If you, for example, do it in MATLAB or Python, it will throw error. It can't invert it. Then what happened? How do we resolve that? So of course we should somehow make X transpose X invertible, right? Not singular. How can we do that? There is a hack in linear algebra used a lot in machine learning, and that's strengthening the main diagonal. Why? Because when you strengthen, what do I mean by strengthening? Adding a very small positive value to the main diagonal. If you do that, so lambda I does that, right? Lambda I plus lambda I adds lambda to the main diagonal of X transpose X. And lambda should be small, it shouldn't be a big number. So it's strengthening the main diagonal. And according to linear algebra, when you strengthen the main diagonal of a matrix, it becomes full rank. And when it is full rank, it is invertible. It will not be singular. Okay. Of course, strengthening this main diagonal reduces the accuracy, because this is not exactly X transpose X. By accuracy here, I mean it will not be exactly as equivalent as linear regression. It will deviate from linear regression, right? Because that's the effect of regularization. So the solution of ridge regression is not equivalent to the solution of linear regression. Now let's see the effect of lambda. What if lambda is too small? The solution reduces to linear regression. What if lambda is too big? Then X transpose X plus lambda I converges to lambda I. It completely forgets X transpose X. So it forgets the task of linear regression. It completely focuses on the regularization term. It forgets the actual cost function, right? So lambda shouldn't be too big. And now let's So again, what was the predicted labels? XB, X beta, right? So X beta, and we replace beta with the solution of ridge regression. This is the predicted labels in ridge regression. Interesting, right?
Is linear regression still very popular right now in machine learning?
Yes, it is, especially in statistical machine learning. What do I mean? In people in the statistics departments who work on machine learning, they love linear regression.
Neural network now.
Yes, we have neural networks, but don't say that in front of the statisticians, because regression itself is an important field in the statistics, in pure statistics. Okay, we have professors on specialized on regression. Okay, and also the regression is not just restricted to this linear regression. We have a lot of things in linear regression that many data scientists and machine learning people haven't even heard of. For example, I don't know if you have heard of sufficient dimension reduction, SDR. I have a tutorial on that. Feel free to read that. So it's called sufficient dimension reduction and kernel dimension reduction tutorial. So kernel dimension reduction is a special case of sufficient dimension reduction. And it says it is used for high dimensional regression, because when you have a regression problem, when you have a huge number of dimensions, this simple linear regression will not work well. So they try to reduce the dimensionality inside the regression, and they call it sufficient dimension reduction. And they say how many dimensions are required for preserving the accuracy and these things. So it has a huge field, and there are, I think, thousands of papers on that. Okay.
In any cases that neural network cannot solve, but regression can solve that.
So is there any problem that neural network can't do? Nowadays, neural networks are very powerful and they can approximate almost all functions. But the problem is that neural networks needs to generalize well. If sometimes they can't generalize well, they get overfitted. If they can generalize well, then maybe for industrial analysis, it might be good. But sometimes data scientists and machine learning engineers can't find out if a regression doesn't work well. But statisticians can figure it out by pure regression methods. Okay. So now let's consider P is greater than 1 again. So we have higher than several, the labels are vectors. Then this is as before, squared Frobenius norm, but the beta, the regularization term becomes squared Frobenius norm of B, matrix B. Okay, let's simplify it. These terms are simplified as before, but the last term becomes lambda trace of B transpose B. If we take derivative with respect to B, these terms are as before, but the last term, its derivative becomes 2 lambda B, right? Now we set it to 0. This 0 is 0 matrix. 0 matrix, right? Because this derivative is 0. This is a matrix. Now rearrange the terms. So these 2 becomes minus 2 x transpose y, bring it to the other side. We'll have these, factor out 2, right factor out B. These two 2's cancel each other. This is a pain in the neck. Left multiply the sides by that term inverse. We'll get this, right? And the prediction will be XB. Okay. Ridge regression is all. Okay. So years ago, although you might think it's very simple, right? But I tried my best to make it simple. Years ago, it was very hard for me to understand regression. But I think when you understand regression, you see that it's very simple. But for me, initially, it was very hard. because I didn't have calculations like these in front of me. Okay, it was hard for me to figure out. So I have collected different calculations of my teachers, myself, put them all together so that it became simple. Okay. Now, Lasso linear regression. I think the hardest among these three is the Lasso, but it's very cool. Okay, it's again related to soft thresholding that we just discussed. Okay, of course, whenever you have L1 norm, you will most probably end up with soft thresholding when you are optimizing it. Okay, as explained before, sparsity is important. I think I already talked about this slide. So we have subset selection. So we can say we have a subset selection regularization term, but we can relax it to L1 norm regularization. We already talked about this slide. Now let's use it for linear regression. So this is the actual cost of linear regression. But let's add L1 norm of the betas as the penalty. All right. This is L1 norm of beta, right? This is exactly L1 norm of beta. So in matrix or vector form, it's like this. Agreed? Where my optimization variable is vector beta, d plus 1 dimensional vector. What should I do? I want to do it, use coordinate descent. What do we do in coordinate descent? We all consider the elements, the coordinates of the optimization variable one by one. What is my optimization variable? Beta. Therefore, you tell me, the elements will be beta j, right? So before that, can I restate equation 21 as this? Can I restate it as this? Why? This is y as before, right? X beta, can I write it as this? Summation of beta k xk prime. What is xk prime? So is the kth column of x. Do you remember x was n rows, d plus 1 columns, right? Consider the kth column of x as I denoted by xk prime. Why do I use prime for it? Because x without prime is like the data point, which are the rows of x, considering the columns of x. Agreed? So I'm considering the features of data xk, right? Agreed? And you agree that it's an n-dimensional vector because it's a kth column and I have n rows. Agreed? Okay. So what is this doing? It says that multiply beta k by the kth column of x and then sum them up over all of the columns. It becomes exactly x beta. It's matrix multiplication, right? Okay. Then this is also the L2 norm of beta. Yes. But let's simplify it further. Why am I simplifying? As I told you, I want to use coordinate descent. I want to write this cost function as the function of beta j. So then I can simply take derivative. Here, it's not a function of beta j, it's a function of beta. I want to single out beta j somehow. Okay. Let's simplify it further. How do we do that? So can I write this summation, break it down into this summation and this? So this summation, I exclude the jth one, beta j, and bring it out of the summation. Agreed? Summation of several things, I exclude one of them, I bring it out of the summation. Why am I doing that? Again, because beta j is important for me. The rest will be constant with respect to beta j. Okay, agreed? Which one?
Is from K is equal
Oh, because I understood. So question is, why is the summation over J equals 1 to D plus 1, right? The reason is that I want to write X beta in as this, okay? X has n rows and D plus 1 columns. Beta has D plus 1 is a D plus 1 dimensional vector. Okay, I'm considering X column wise now, column by column. Xk prime means the kth column of X. So this matrix multiplication, I can assume that I'm multiplying every element of beta by every column of X, and then I sum them up. 20. Okay.
beta J.
Oh, now your question is this, right? Okay. Do you agree? For example, let's write this down like this: beta 1 x 1 prime plus beta 2 x2 prime until beta d plus 1 x d plus 1 prime. Do you agree? I can. So I am considering. I'm assume J is 2 here. Considering this beta 2 x2 prime, bring it out. So I'm saying that sum everything except that one plus that one. Here I'm doing this. Sum everything except k equals j. Bring that out of the summation. Let me say it in more clearly for you. So I have beta 1 x1 prime, beta 2 x2 prime. Somewhere in between, I have beta j xj prime, beta d plus 1 xd plus 1 prime. Agreed? Can I write it as this? Beta 1 x1 prime until beta j minus 1 xj minus 1 prime plus beta j plus 1 xj plus 1 prime until beta d plus 1 xd plus 1 prime plus beta j xj prime. This is exactly the summation that I have here. This summation is exactly this summation. And this term is exactly this. I'm just taking this out of the sum. You didn't get it? So how should I? You get it? Okay. But let me know if you didn't understand. Did you understand it? Honestly? Okay. So from equation 22, we came to equation 23. The reason is that beta j is important for me and the rest will be constant. Okay. So I'm repeating what we had. Now, this I know is constant with respect to beta j. Let me denote it by z. Okay. So it will be like this. I can write it as this, right? Also, I can write it element-wise. What is this? It's lambda summation of whatever we call it, j equals 1 until d plus 1, absolute value of beta j. Okay. Now, I want to only consider, let me write it in this way, lambda summation of j plus 1 d plus 1, absolute value of beta j. In here, or here, doesn't matter, I want to only consider beta j because of coordinate distance. Z is constant with respect to beta j. I write it as z, right? This is as before, like this. This term, I only consider jth element. The summation goes away. Don't you agree? You can write it as this. You can write it as lambda summation of j equals 1 to d plus 1, where j is not equal to Let's denote it in another way. K from 1 to d plus 1, where k is not equal to j, beta k, sorry. But why have I dropped this term? Because it's a constant plus some constant. Do I care? Minimize f of x plus some constant with respect to x, or minimize f of x with respect to x. They are equivalent in terms of argmean, right? In terms of argmean, they are equivalent. And so I've dropped those other terms. I have these. Now everything was, I have beta j's. So let's simplify this cost function. Let's simplify this cost function. What happens? What is this? Everything, a squared L2 norm of something is that thing transpose that thing. So I have this transpose this plus this term, right? Then what happens? I apply the transpose inside in the elements of it. So I have Z transpose. Also, beta J is a scalar. Nothing happens. But XJ prime transpose I will have. What about this? This is the same. Okay. Also, this is like this. Now, I have 4 terms here, right? Multiply the terms together. Z transpose Z minus beta J Z transpose XJ prime minus beta J XJ prime transpose Z, these and the last term, okay? Now, we simplified the cost function. Let's take derivative with respect to beta J for the sake of coordinate descent, right? Because I'm in coordinate descent, I only consider the jth element, right? One by one. So with respect to beta J, what is this? Let's take derivative of this. The first term is constant with respect to beta J, goes away. The second term is linear with respect to beta J. It's this. By the way, this derivative is very simple. Why? Because it's a derivative of a scalar with respect to a scalar. If it is a scalar, that's exactly high school derivative. This is also derivative linear with respect to beta J is this. This is quadratic with respect to beta J, so it becomes 2 beta JD, right? What is this? Derivative of absolute value. We just talked about it. It's sine function. It's this sine of beta J, right? Now, what happens? Here, the only difference is that, do you agree that a vector transpose a vector? I can, so A transpose B, when A and B are vectors, I can write it as B transpose A, right? Agree? So here, I change the order of these two. Okay? So far clear? Now what happens? What these two are equivalent, so it becomes minus 2 of these. And the rest as before, set it to 0. We took derivative, set it to 0, as in high school. Okay. This is a scalar 0, right? Now what happens? Now what happens? We can write this as 2 equations. If beta J is greater than or 0 or less than 0, then the sign of beta J will be +1 or -1. Agreed? So if beta J is greater than 0, then we can rearrange the terms. Beta J becomes this. If beta J is less than 0, beta J becomes this. Okay? So we had this. By the way, so this is what we found. Sometimes they put 1/2, because sometimes in the literature, rather than this equation 25, you see equation 26. I don't want you to get confused. The reason is that they have put 1/2 before the actual cost function. If you do that, and you do exactly the steps that we did, you will end up with equation 26. Okay? Doesn't matter. Either 27 or 26. Also, sometimes you might see equation 27. What do they do for that? If the columns of the matrix X are normalized to have unit length, so they sometimes normalize the columns of matrix X, then do you agree that xj transpose xj prime transpose xj prime becomes 1? Because that's exactly L2 norm, the squared L2 norm of xj prime, and that's a squared length of xj, the jth column of X, right? It's 1. So these denominators go away, and they simplify to this equation 27. Okay. What is this? This or this or this? 25, 26, or 27, whatever. These are soft threshold. Assume the last one. This is exactly soft thresholding. So consider the plot of beta j with respect to xj prime. If beta j is greater than 0, I'm here, right, in this region. Then I should use this equation. What is this? This is a line with respect to xj prime, right, with the slope, whatever you say, z, right, and minus with the intercept lambda. This one is exactly this line, so I'm in this region. Now for beta, so this must be here, greater than 0. For beta j equals 0, I should connect these two plus together. So I will have the. Now analysis is exactly the same as analysis of L1 norm regularization that we had. If what happens if xj prime, the jth element of X, the jth column of X, right? What do I mean by jth column, by the way? One of the features of X, right? One of the features of X is not that much important. It's very small. Set beta for that to complete the 0. Make it a sparse. Otherwise, shrink it. So in these regions, as you see, they have been shrunk. Right? So shrink it, but if it is much small, completely put it to 0. That's for, as a result, the vector beta becomes a sparse. Many of the elements of beta will be 0, will be set to 0. Did you understand? So if you don't use regularization, it's supposed to be something like this. This line. For this region, it's shrinking to here. It's making beta smaller. For this region, it's shrinking it to here, making absolute value of beta smaller. For this region, it's making beta exactly putting it to 0, setting it to 0. Right? This comparison I already talked about, but again, Tibshirani showed this comparison for Lasso regression. So said that when we use, so what is this, by the way? Figure A for regression is ridge regression. Figure B is Lasso regression, where ridge regression uses L2 norm regularization and Lasso regression uses L1 norm regularization. Agreed? Acknowledgements. For more information on linear regression, see the book of Hasty, Tibshirani, and Friedman, The Elements of Statistical Learning. Again, another one is the Statistical Learning with a Sparsity, the Lasso Generalization by Hasty, Tibshirani, and Wainwright. Also, some slides of this slide deck are inspired by teachings of Professor Mu Zhu at the University of Waterloo, Department of Statistics, and Professor Huda Mohammed-Zadeh at Sharif University of Technology, Department of Electrical Engineering. So these are the references. Okay, let's have a break and come back at 9:10. Good? Thank you. Okay, so you were saying there was a question. So you said yes. So in Lasso regression, we have if xj is a small, shrink it. If it is too small, set beta j to 0. Then When beta j is 0, it means completely disregard that direction. Yes, if it is too small. When beta j is 0, what does it mean? Because we have x beta, right? When beta j is 0, it means that completely ignore that feature. Because it's xj is too small. I don't care.
The label, I mean the prediction. By doing this.
So it, because of actual cost function, it predicts it. So it is minimizing the error of regression. Also, it tries to make it sparse because of that penalty. That's it. As we have the actual cost, it already has minimized the error of prediction. By the way, I wanted to tell you one important thing for you to better understand linear regression. I think what I'm going to tell you gives you an insight. Okay. So B was what? X transpose X inverse X transpose Y. X transpose X inverse X transpose Y, right? In linear regression. What was Y? The predicted Y hat, whatever. It was what? It was XB. On the one hand, we had this, right? On the other hand, let's recall linear projection. What was that? Assume I had X. I said U transpose X. What does it do? Projects the columns of X onto the column space of U, right? Do you remember? This X was what? For example, it was D by N because I had put them column wise, right? This U was P by D, am I right? Or no, sorry, D by P, I apologize, D by P. So U transpose was P by D. So the whole thing was P by N, and we said that it is projecting the columns of X onto a subspace, P-dimensional subspace. Do you remember? Now, here I said X is put column-wise, right? What if I put X row-wise? The same way that we do it in linear regression. What happens to linear projection? My X is N by D this time. So, okay, N by D. Then my U is, for example, D by P. Then what happens? So I should multiply it in this way. U is D by P. The whole thing becomes N by P. So this is also linear projection, but for row-wise. What does it do? This projects, so this one projects the rows of X onto the column space of U. The left-hand side, this one projects the columns of X onto the column space of U. This projects the rows of X onto the column space of U. In this one also, after the data points, after the projected data points are stacked still column-wise. In this one, the projected data points are stacked row-wise. So again, let me repeat. In this left side, this one, the data points before projection are row-wise. After projection are row-wise. Sorry, this one, sorry, apologies. In this one, the data points before and after projection are column-wise. In this one, the data points before and after projection are row-wise. In this one, the columns of data X are projected onto the column space of U. In this one, the rows of X are projected onto the column space of U. So far clear? Now compare this one with this one. So linear regression is just a linear projection of X onto the column space of B. As expected, because linear projection and linear regression are both linear. So you can interpret linear regression as a linear projection. That's also related a bit to sufficient dimension reduction, because you can see linear projection as a dimensionality reduction. Do you agree? What is B here? D plus 1 by P. P is the dimensionality of the labels. X is N by D plus 1. The whole thing, Y hat, becomes N by P. So basically, what are you doing? You are projecting the dimension, the data points onto p-dimensional subspace, where P is the dimensionality of labels. Let me repeat. So here I said, what was it doing? Projecting the rows of X onto the column space of U. Here also projecting the rows of X, which are the data points, onto the column space of B, which is a subspace, p-dimensional subspace. And P is the dimensionality of labels. Interesting. Right. Another insight, let me tell you very fast. I don't have enough time. So another insight. Regression can be divided into linear regression and non-linear regression, right? The regression is a task. We have methods for regression, right? So we have linear methods for regression. We have non-linear methods for regression. Some of the non-linear methods for regression are using neural networks for regression, using random forest for regression, using decision tree for regression, 10 years neighbor for regression. All of these are non-linear regression. Okay. So consider a neural network. Now I give you a puzzle. Assume, consider it U1, U2, U3, 3 layers of neural network. And in here, my loss is mean squared error of my y hat minus y. Y hat is the output of neural network, and y is the actual labels, right? Then assume even if my labels are multidimensional, then I will have matrix y hat minus y, matrix y. Okay, doesn't matter. And it will be Frobenius norm squared. Assume I don't have any activation function. I don't have any nonlinear function between the layers. Or my activation functions are linear. Okay. If I solve this neural network by backpropagation, the loss is mean squared error. What will be the solution? This neural network, the solution of it will become exactly linear regression. Why? Because in linear regression, we are minimizing this cost function exactly. And also, the method is linear in linear regression. However, in here, it's neural network, but it is not nonlinear. It's a linear network. Why? Because I don't have any nonlinear activation functions. And let me prove to you why it is linear. What is this? The output y hat or y whatever. Assume this is input X. It will be U1. So depending on whether you consider it row-wise or column-wise, let me consider it row-wise. X, U1, U2, U3, or the other way around. I need to calculate. Either it's X, U1, U2, U3, or it's X, U3, U2, U1. Okay, doesn't matter. Do you agree? And I don't have any nonlinearity between them. If I had nonlinearity between them, it would be like this: F1, U1, F2, U2, and F3, U3, where F1, F2, and F3 are the nonlinear activation functions of first, second, and third layers, right? But I don't have any nonlinearity. So it's this. Do you agree that I can consider it as a U4? Let's define U4 as U1 times U2 times U3. Here I can't because these are non-linear. Then it becomes XU4. Let me rename it to beta, X beta. This is exactly linear regression. Okay, that was another insight I wanted to get you. Let's go to the next topic. Linear projection is used in most of the linear methods in machine learning, such as PCA, such as FDA, such as linear regression. Almost, I think, if I'm not wrong, you can see all of the linear methods in machine learning as linear projection. It's from some space to another space. Because if you truncate the projection matrix, it's useful for dimensionality reduction. If you don't truncate it, it's useful for rotation. Okay. And you know that linear transformation, you can see it as an affine transformation. In affine transformation, you have rotation and translation. That's exactly what we have in affine function. We have ax plus b. A is the slope, b is the intercept. Here also we have rotate plus intercept plus translation, right? Did you understand dimensionality reduction? So if I don't truncate it, it becomes rotated. Sometimes, such as analysis of the regular L2 norm regularization that we had minutes ago. What did we do? We rotated. We did some transformation and we rotated it back. So if we don't do that transformation, it seems that we haven't done anything. But we rotated that. We did some transformation. We rotated it back. But the rotation has a lot of applications in image processing and computer vision also. Any other question before we continue? What do you mean?
Why do you need the rotation?
We need rotation. So I'm saying that sometimes we actually need the rotation, such as when we want to rotate an image or we want to rotate a data point for different tests. It is especially used a lot in image processing, computer vision, these things. You want to rotate a camera model. Camera is facing like this, you rotate it. But sometimes it appears, such as what in our analysis of L2 norm regularization, it appeared that we had rotation. And sometimes we use that for dimensionality reduction if we truncate that.
Image, what the image will be.
When we rotate an image, the image rotates. Yes, the image rotates. For example, you have a human like this, then it becomes like this. Right? You rotate. So you can have rotation. Also, you can. I strongly believe that machine learning and computer vision are closely related. Closely related. Yes, for data set preparation, for data augmentation. So, okay, linear and quadratic discriminant analysis. So we are entering classification now. Okay, this is one of the most fundamental algorithms for classification. And this is a linear. So linear discriminant analysis is a linear classifier. Quadratic discriminant analysis is quadratic, is non-linear. Okay, so optimization for the boundary of classes. Assume we have a data set of instances x1 to xn and their labels y1 to yn. Here the labels are scalar and they are discrete, so it's classification. Class 1, class 2, class 3, right? With sample size n, the number of points is n. Here, I mean training data sets, okay, n. And dimensionality d. So dimensionality of data points are d-dimensional, but the labels are scalar, which are class labels. We want to classify the space of data using these instances. So these LDA and QDA, they partition the space. What do I mean by partitioning? Assume I have these classes. and they are linearly separable. If they are not linearly separable, then LDA won't work well, because a linear classifier always has a linear boundary, okay, decision boundary. So assume LDA does that, and it partitions the space into two parts like this, right? And what does QDA do? QDA does something like this, quadratically. Okay, it's a quadratic function decision boundary. Do you agree? It's like a bowl. Okay, so linear discriminant analysis and quadratic discriminant analysis, LDA and QDA, are two well-known supervised classification methods in a statistical and probabilistic learning. They are probabilistic classifiers. Okay, first off, here by LDA I don't mean Fisher's discriminant analysis, Fisher discriminant. We will cover FDA or Fisher discriminant analysis in a few lectures. This is LDA. Okay. Yeah.
For the same data set, it's linearly separable. So
Yes.
which one is better?
Depending on your data, sometimes yes, but this, consider this. Assume your data is like this. Of course, QDA is better for this. QDA will fit something like this. But LDA will tell you this. LDA will have error, because here for a test point here, I suppose that this is star, but LDA will tell you it's a circle. Okay, depends on the pattern of your data. Okay, first suppose that the data is one-dimensional for now. Okay, assume we have two classes with the CDF. What was CDF? Cumulative distribution function. So it means that increase, so always integrate or sum up the probability until now, so far. Okay, if you don't know what CDF is, just Google it, it's easy. F1 and F2. Okay, and PDF or probability density function is the derivative of CDF. Simply assume this is the PDF, the CDF becomes like this, because I'm always summing up the probability, so it goes to 1, from 0 to 1. Okay, so I have these small f1 and f2 are the PDFs, probability density functions, and capital F1 and F2 are the CDFs. Okay, anyway, so assume the two classes have normal or Gaussian distribution. Okay, this is assumption that we make in LDA and QDA. Okay, which is the most common and default distribution in the world. Even the cells in our eyes work like a Gaussian distribution. They actually work like Gabor filter. I don't know if you have heard of Gabor filter, Gabor. Gabor filters, you can see them, they are very similar to Gaussian distribution. Okay, the mean of one of the two classes is greater than the other one. So here, as I said, assume this is scalar data. So in scalar data, I can say the mean is greater than the other one. So mu1 is less than mu2, right? An instance X, which is a scalar, belongs to one of the two classes, of course, right? So if it is in class 1, then it belongs to the first Gaussian distribution. If it is in class 2, it belongs to the second Gaussian distribution. And by this, I mean sampling. X is sampled from that distribution, right? C1 and C2 are the first and second classes. Okay. For instance, X, we may have an error in estimation of the class it belongs to. Do you agree? So we might have error. And I think you can guess. What do we want to do? We want to minimize the error, right? All machine learning is minimization or maximization of something, right? So at a point which we denote by X star, the probability of the two classes are equal. Do you agree? For example, like this, these are the two Gaussian distributions. Somewhere they intersect, and at that point, the two probabilities are equal to each other, like here. LDA tries to find that point. LDA and QDA try to find this point where the two probabilities are equal. Do you agree that that point can be the decision boundary? Right? So as we have mu1 is less than mu2, right? Like in this figure, we can say that X star is between mu1 and mu2. Agreed? Therefore, if X is less than X star, then it should belong to the first class. If X is greater than X star, it should belong to the second class. Therefore, if I say that if I estimate X, if X is less than X star and I estimate it to be in the second class, it's an error. And if X is greater than X star and I estimate it to be in first class, that's also an error. So let's minimize that error. So the probability of error is the probability that X is greater than X star, but I say X belongs to C1. Or X is less than X star, but I say X belongs to C2. And I need to sum these two probabilities. Okay. We know that the joint distribution can be written as conditional distribution and this. So P of A and B can be seen as P of A given B times P of B, right? Therefore, I can state these two probabilities as these. Probability of X greater than X star given that X belongs to C1 times probability of X belongs to C1. What does it mean? What does this term mean? X is actually in the class 1, but it falls above X star. This means X is actually in class 2, but it falls before X star because I choose the X star. So maybe I chose it badly. Then this will increase this probability. Okay. Also times these priors. Great. By the way, this is called likelihood or class conditional. This is prior of the classes. Okay. We want to minimize this probability of error with respect to X star. So my optimization variable is X star, right? So we had this. Now let's simplify. So what is this? Do you agree that according to the definition of CDF, what is this probability of X belongs to C1, but less than C? It's exactly the CDF of C, CDF1 of C. So again, let me repeat. First off, X belongs to C1, so I should consider the first Gaussian distribution. Less than C, so I should consider the CDF of first Gaussian at the point C. Therefore, now I consider this, which has appeared here. Point C is a general point. Now I'm gonna use X star as C, okay? Probability of X, so we know that probability of X less than, according to this formula, X less than X star, where X belongs to C1 is F1 star of X star. Therefore, the other way around is 1 minus that. Probability of X greater than X star, and X belongs to C1 is 1 minus F1 X star. What about this term? This is exactly the CDF, the second CDF at X star. Agreed? Okay. Also, what about these priors? I denote them by pi 1 and pi 2. I'm denoting them. These are the priors of the classes. Okay. So if I put these equations inside the probability of error, I will have this, right? put equations 7, 8, 9, and 10 in this. You will get equation 11. I want to minimize this probability of error with respect to x star. Right?
Regression minimize the absolute error, right? Here we minimize the probability.
Yes.
What's the
What do you mean by so here we should minimize something which is bad for us in machine learning, or maximize something which is good for us. Here, what is bad for us? The probability of error. So you depending on what cost you choose, you will end up with different algorithms. So if you choose this cost, the probability of error as your cost, this one, you will end up with an algorithm which they named LDA. If you change your cost, you will end up with another algorithm. And if it is a new cost, you can name it yourself and publish it. So we will see different algorithms in machine learning in this course, each of which has some cost. We'll see. Okay. And you will believe in my statement saying that all machine learning is optimization. Okay. So derivative of this probability of error with respect to x star, what is that? What is this pi1 is a constant multiplier, so we'll have this. What is the probability of this? This 1 is a constant, goes away with respect to this. Minus comes here. What is the derivative of CDF? Is PDF. So PDF of x at the point x star. What about this? Derivative of f2 capital becomes f2 small. For the PDF with pi2, now set it to 0. High school. First order optimality condition. Rearrange the terms, you will get this. Right? We can obtain that equation in another way. What is that? I think it's easy for you to understand. Rather than minimizing the probability of error, let's say the decision boundary is where the posteriors are equal to each other. What is the posterior? This is posterior. This is called posterior. So let me add a page. Recall preliminaries, Bayes rule. Bayes rule. Probability of, just give me a sec. Yes. X belongs to class given X is probability of X given class, right? Probability of class over probability of X. They call this likelihood or class conditional. This is prior of class. This is prior of data, the whole data, regardless of classes. This is called posterior. I think it's obvious for you why. This posterior, the name, posterior and prior, they came from Latin, okay? Posterior means post, after. So after I see the data, what is the probability that it belongs to this class? Prior means I know it beforehand, right? In prior. So the probability of class in beforehand, the probability of data beforehand. They also sometimes call it marginalized probability. Why? Because why? The reason is according to the law of total probability, recall preliminaries, you can write P of X as summation of Px given C, PC over all C's. You are marginalizing over classes, over X, whatever you call it. We are marginalizing it for X, right? As a result, we also call it marginalized probability. Doesn't matter. I was talking about posterior, prior, and so I told you posterior, prior, and likelihood is another name for probability, right? So given the class, what is the probability of my data? And I also said this in the deep learning course. These words have been borrowed by mathematics from philosophy. In centuries ago, Immanuel Kant who was a philosopher, proposed in his epistemology, proposed that we have several ways to interpret the propositions. Okay, in epistemology in philosophy talks about whether a proposition is true or wrong, and also whether it's senseful or nonsense. Okay, so Immanuel Kant said that we have some propositions are prior propositions, so we know them beforehand, even without experiencing the world. And there are some things which are posterior, which we understand them by what? By experiencing the world. In Latin, they called it a posteriori, and a priori, if I can pronounce it correctly. So these words came to mathematics, borrowed from philosophy. Okay. Now, and it also appeared in Bayes' rule. Okay, so let's continue where we were. Okay, so now we can say the decision boundary is where the posteriors are equal to each other. Set them equal to each other. In this way, you don't need to do optimization. We just solve this. Let's use the Bayes rule. So according to the Bayes rule, this is the posterior, right? So I can rename it to the F1 of X. Why? This is exactly the PDF for class 1, right? F1 of X, prior pi of 1, class 1. What is this? Some marginalization. I'm marginalizing in the denominator. Now, if I set these together to each other, the denominators are equal to each other, so they cancel each other. So only the numerators of the Bayes rule will be equal to each other. This equation 15 is exactly as equation 12. So in two ways we can end up with this equation. Now, so far we assume that the data is a scalar. Now let's assume it's multivariate data. So it is a d-dimensional vector, for example, with dimensionality d. Then the PDF of the Gaussian distribution becomes a multivariate Gaussian distribution, right? So the mean becomes a vector and the variance becomes a covariance matrix. So f of x, this is the PDF of Gaussian distribution. The formula for PDF of Gaussian distribution, mu is d-dimensional, x is d-dimensional, and sigma is d by d. Okay, this is the determinant of the covariance matrix. Okay, and pi here, don't confuse it with pi 1 and pi 2. Here is the pi number. Okay, and now let's use this formula in the equation that we had. F1 pi 1 equals F2 pi 2. So F1 and F2 are Gaussian distribution. If I do that, I will have equation 17. Okay. So here I'm using sigma 1 and mu 1 for first Gaussian distribution, and mu 2 and sigma 2 for second distribution. Now linear discriminant analysis. So far was preliminaries for LDA. Okay. So LDA uses that what we found, but makes an assumption. Says that I assume the covariance matrices of the classes are the same, are equal to each other. So sigma 1 equals sigma 2. Let me denote it by sigma. Okay. So let's replace sigma 1 and sigma 2 with sigma in that equation 17. So we'll have this. Now these are sigma, right? When I do that, interestingly, these terms are equal to each other. So I can get rid of them. Now you understand why LDA makes this assumption, because these are a pain in the neck terms, right? So they go away, and I will have this expression. So I have exp operator, exponential operator, pain in the neck. Whenever we have exponential operator as a pain in the neck, what should we do in machine learning? We use the opposite operator, logarithm, natural logarithm, to get rid of that. So we take logarithm, natural logarithm from the sides. We know also that the logarithm of AB equals logarithm of A plus logarithm of B. So I will have this term plus logarithm of pi 1. And this term inside plus logarithm of pi 2. We can simplify this term as this. So here we have these terms, right? These two terms, right? Which are in the same format. Let's consider one of them, such as x minus mu1 transpose sigma inverse times x minus mu1. Let's simplify. So this transpose I applied on the elements. I will have x transpose minus mu1 transpose. Agreed? Then I have how many terms? 4 terms. So 2 terms here, 2 terms here, and 1 term here. Multiply the terms to each other. What do I mean? First, what we'll have x transpose sigma inverse minus mu1 transpose sigma inverse. So I have 2 elements here and 2 elements here. So x minus mu1. Multiply the terms to each other. Agreed? Did you understand? So I will have these 4 ones. So x transpose sigma inverse x transpose sigma inverse mu1 transpose sigma inverse x, mu1 transpose sigma inverse mu1. Agreed? Okay. Now what happens? By the way, I never memorize these things. I figure this out when I'm explaining this to you. Okay, just give me a sec. Okay. This one, this is a scalar, right? So it's equivalent to its transpose. So this is equivalent to mu1 transpose sigma inverse transpose x. Let me write it down so you don't have space. Let me add a new page. X transpose sigma inverse mu1. X transpose sigma inverse mu1. I want this is equivalent to its transpose because it's a scalar. So I can write it as mu1 transpose sigma inverse transpose x transpose transpose. X transpose transpose is x. Sigma inverse transpose is sigma inverse because it's a diagonal. Sorry, symmetric. It's a sigma is a covariance matrix, symmetric, right? So when sigma is symmetric, sigma inverse is also symmetric. Mu1 transpose, so it becomes mu1 transpose sigma inverse x. Interestingly, we have it here too. So we have 2 of these. So I have -2 mu1 transpose sigma inverse x. What about, so this term, I have written it here. This term, I have written it here. So far clear? I have 1 more minute. So let me just say this a little bit, finish this slide and we'll over. So here now, let's put equation 19 in what we had here. Okay. If we put that, we'll have this. Okay. So this is exactly what we found here. And this logarithm of pi 1 and this plus logarithm of pi 2. Agreed? Now we can simplify this. Interestingly, these two cancel each other. Again, because of assumption that sigma 1 equals sigma 2 equals sigma. now I think you can understand how the designers were thinking. Let's simplify it so we get rid of these terms. Then we bring the sides, so we rearrange the terms. I have this mu1, this one, also this one. What about these two? I bring them here, but interestingly, I can write it in this format. So I can, just give me a sec. Sorry, these two. Yeah, these two. Do you agree that I can factor out sigma inverse, and also I have transpose? So what is this, by the way? It's because mu2 minus mu1 transpose sigma inverse, because transpose reverses the order. So these two, I'm factoring out sigma inverse. I'm also applying some transpose. So it becomes this. And what about these two? Logarithm of something. When I bring one of the logarithms to the other one, to the other side. So we know that logarithm of A minus logarithm of B, I can write it as logarithm of A over B. So I can write it. Where did these 1/2s go? I multiplied the sides by 2. So I have 2 here, and those 2's go away, and I have 2 here also. Equals 0, because I have brought everything to one side. What is this? Equation 220. Is it linear with respect to x? Is it quadratic with respect to x? It's linear with respect to x. Consider this as Benjamin transpose x plus Jack or Jennifer, whatever. Benjamin transpose x plus Jennifer equals 0. What? No, this term is completely constant with respect to x. That's why I called it Jennifer, right? This is constant with respect to x. I called it Benjamin. Benjamin transpose x plus Jennifer equals 0. It's an equation of line with a slope Benjamin or normal vector Benjamin and intercept Jennifer, right? So equals 0. That's in the format of A transpose x plus B equals 0. As you see, A or here Benjamin is a vector, d-dimensional vector, because x was d-dimensional. But Jennifer or B here is a scalar. It's equals 0. That's exactly line. Hence the name linear discriminant analysis. Because the decision boundary here this is a decision boundary. It's a line. Okay, we will continue this also quadratic discriminant analysis in the next session. Thank you.